final keynote of LambdaConf. How many of you would love to design your very own programming language, either in retirement or maybe if you're super lucky before? What? Get your hand. Okay. Not everyone apparently is as crazy as most of us are. But as a programmer of more than 30 years, I'm always thinking about what sort of language I would design. Of course, I've never had the chance to do that. But our next keynote speaker has. His name is Jonathan Blow, and you might know him from Braid, an extremely successful independent video game, or Witness, another extremely successful independent video game. And his time in the trenches has informed his perspectives on programming. And unlike many of us who just dream about the day one day when we're retired and we can invent our own crazy programming language that solves all the world's problems, Jonathan actually had the chance to do that. And tonight, we get a chance to peek into his mind and explore the design decisions he made in Giant, try to better understand why he made these design decisions. So this is going to be extremely exciting. In a moment, I'll ask you to clap and welcome him to the stage. But remember to stick around afterwards. There's going to be some closing remarks and, of course, a conference dinner. So don't run out when you see the final slide. Stick around. There's more to come. All right. Please help me welcome Jonathan Blow to the stage.
All righty. I have two laptops that I'm going to have to juggle here, so nobody in the room knew I was a juggler, I guess, but that's what's happening. All right, this one. So the reason I'm juggling two laptops is, this is a functional language conference, and I don't usually hang out in these circles, so I figured for cred, I had to do my slides in Emacs. So that's where we're at. We aren't going to have letters that fly around and change places or anything. But yeah, I'm here to talk about a programming language I've been working on for a long time. This project has been going for more than 10 years, and there's a lot to talk about. And I feel like there's sort of two main areas where I could focus my attention in terms of explaining what this thing is. One, among these crowds, many people may wonder, why would you think it's a good idea to make another systems language? Haven't we moved beyond that technologically, right? Oh, you're manually managing memory like it's 1970. Why is that a good idea? Why would you even want to do that? And I'll preemptively say the same things that everyone says to start, which is for performance and simplicity. In the games industry, our performance demands are very tight. But a lot of what I will do in the rest of this talk is to justify why that's an okay trade-off to make. And you don't need to agree with me on that. I don't expect most people in the room to 100% agree with me, but I'm at least going to illustrate as much of the thought process as I can, and what are the design decisions that went into making a better language with manual memory management? Because if you're going to make just another language that does the same thing as like C++ does, it's probably not that interesting, right? So you have to have a new angle on it. Now, in terms of this design process, I did take some inspiration from functional programming languages in a number of ways, and that'll be my other touch point for relating to the general perspective here. And there's again a number of ways in which this is true, but I'll talk about the two main ones. One is embracing this idea that a program is defined by the text of the program, which sounds tautological, but is actually not true in the systems programming world, right? And this is like a weaker version of my program as a function, right? But it's less extreme. It's like my program, there's only one way to interpret this string of text, right? And the reason why I say this is not true in the systems programming world and not obvious is, those of you who know C or C++ know that you can't actually compile a C or C++ program without another programming language, right? Because it's broken into chunks, and there's no specification of what those chunks are or how they relate to each other. So you have this thing like a makefile or a build process language or whatever to give meaning to the program, right? So the program is not complete in itself, right? And then that gets even more complicated as you go from operating system to operating system, and you need to write totally different build environments to like do the same things in different places. And then there's like, you know, crazy abstruse like linkers, embedded linker command languages that nobody knows exist anymore that become important. And before you know it, you're using like 5 programming languages just to make your programming language build. And if you like DSLs and stuff, you might be enthusiastic about having to use 5 programming languages. But for me, it's always been a pain in the butt. And so I want my program to be as well defined as possible, right? I want to be able to take it somewhere new and it just works, right? And then the second place that I'm going to use it as a touch point is this idea of code as data. You know, a lot of people, especially coming from the Lisp world, love to say like, code is just data, man. And it's a weird thing because on the one hand, literally nobody was ever confused by that, right? Like the abstraction of the Turing machine is like code is data, or even in the early days of actual modern computers, before we had programmable computers, you had hard-coded computers where you could like input parameters, and we had to invent the idea of interpreting data in this way that makes a process happen. So nobody was really ever confused about this, but I think the reason Lisp people are excited about it generally is because of macros, because they have more powerful macros than anybody else at the time or whatever, and you could manipulate a higher level version of data, right? That's what's really meant by code is just data. And so I'm going to go through some, for a systems language, very high levels of viewing your code as data. All right, so I'm going to just start demoing stuff. And you know, this project, I think of it as reality-based design in the sense that it's informed by my experience of building things in the past, and also you know, by the problems that I'm having from day to day and what we're working on right now. If we want to get a little volume from the HDMI, that would be great for mood. If we don't, that's fine too. But this is the current project that I'm working on. This is it's about a 300,000 line program. Depends if you count, you know, white space and comments or not. But that's equivalent to like a substantially larger C++ program because it's a higher level programming language. But it's a non-trivial program. This is a commercial quality video game. So I'm like this little guy, I can run around, I can like solve a puzzle by pulling things around, and you know, like these monsters attack each other and whatever. There's a ton of game mechanics in the game. I screwed up and died, I can undo. So there's like a whole bunch of game stuff, right? And then there's a whole bunch of other stuff that developers have, right? So like there's an editor in here, and I can go around the scene, right, and move stuff around and like scale things and copy paste them and undo all that. So everything that you see here is in this programming language, including all these little widgets, right? Like I select an entity and it's got all these text inputs, right? I can change the whatever, right? So non-trivial project is the point that I'm trying to get across. And we'll keep coming back to it. Because we worked so hard on making it look nice, I'll just show a few more. I'll show a few more nice scenes just for variety, like, that's nice, and that's nice. And, but yeah, basically it's a puzzle game. So it was great that we had a puzzle intro. Okay, so I'm just going to start talking about how this compiles and the crazy sort of architecture that I ended up with, which is not exactly where I started out. Where this project started out was this fundamental question: what are you going to do that's different from other systems languages? And one of my answers was, well, you know, I want to understand my program better, and the way that I want to do that is I want to have compile time execution, because if you have a lot of code running at compile time, you can use that code to understand your program in some way. And the question is like, what is that way? And the answer that we came up with is we have these things called workspaces, which is basically a separate container, right? You can think of it as a container in Unix land or something, but a programming language version of that, or like a module space or whatever your favorite terminology is. And inside that, you can compile separate programs, but they can see each other, right? Like little nested dolls or whatever. And the way that works in the modern version of the compiler is as soon as you compile anything, right? So, I might compile this program by saying, sorry for the Windows backslashes, but that's where we're at. Can you see? I wish the font were bigger, but it's fine. So if I do this, right, I'm just compiling the game. It took, 2.3 seconds. That's a full build of a 300,000 line code base, which means that iteration speed is pretty high. That's slower than I wish it were, and it's slower for our target speed for the final compiler. But, so when you do that, when you type that command, what happens is obviously a compiler binary starts up. But the very first thing it does when it starts up is it loads this thing called default metaprogram, which is a user space program that you are able to replace. And I'm just going to flip through this pretty fast because, it's about 500 or 600 lines, but this is actually the control program for the compiler. So like, it handles command line options, right? This kind of code looks, despite the fact that it's in a language nobody here uses, this kind of code is pretty obvious in terms of what it's doing. We do some stuff based on arguments, and there's like a plugin system and whatever. But you can replace this if you want, or you can have another program running inside it and all that. And this provides us with a great degree of flexibility. Now, one structural element that's going to become important in what we see soon is after we do all this setup, we go into a loop, right? We call this thing compiler begin intercept that says, hey, I now want to intercept. This W is this workspace that I set up with the target program, right? So I created that workspace. I said, our program is going to live there. I set options on it. I told it what starting files to start with, right? And we're just going to say, okay, now it's go time. We're going to compile. And we load our plugins. And then we call this thing called message loop, which we're going to look at. And then we're done. We say end intercept, and we're done compiling, and the executable gets written out. So the message loop right now, the one in the default metaprogram, is very simple. It says, hey, while forever, let's see if the compiler has a message for us. If there is a message, if it says complete, we're done compiling, and we can finish. Otherwise, let's just give it to all the plugins. All right? So what are these messages? These messages are information about the program as data. And I will show you in, honestly, not that much detail because it's a big file. It's a 2,000-line file, but there's all these data definitions for what that means. Here's the options that we would set. And there's the plugin struct. And here's the messages. So these are the types of messages that we could send you. There are things like, hey, the program's opening a file. The program's importing a module. It tried to import a module, but that failed. Do you want to try to provide the module? We're changing our phase of compilation. I'll say what those are. Hey, we type checked some code successfully. Here's what was type checked. Compilation is complete. And then, a couple things at the end, and performance report, which we'll get to at the very end of the talk. And the compilation phases are stuff like, hey, we parsed all the source code. We type checked everything that we can. And the reason that's not everything in the program is because we do a lot of code generation. So you may have things in your program that are waiting for definitions to appear in order to acquire meaning. We built all our bytecode. We're about to write the executable, and we wrote the executable. And you just get all these messages into an arbitrary user space program that you wrote, that you can do anything with, right? So I'm going to show the metaprogram for that game that I just showed. It's about 1,400 lines. Again, we're going to flip through it really fast. It basically shells out into a completely different programming language to do that. And the philosophy here is we don't ever want to do such a thing because we want to be as simple as possible and give you a language that's as powerful and expressive as possible. So everything you see is all in the same, there's no like meta language is what I'm saying. It's all the same language. So here's a bunch of code. I don't know, what did I want to show you? There's a few more capabilities that we do in here with this message loop. So for example, there's a little command shell inside. Can't type right now for some reason. There's a little command shell inside the game that you use to like, oh, go to this level or whatever. There's a bunch of commands. And the way that you register a command is you write a function and you tag it with a little note that says, hey, register this command. And one of those messages that tells you, hey, everything got type checked, you can then search for things that have notes on them, right? And register those in an array. And then down at the bottom, we generate code from this, right? So down here, we're like, oh, that's an error report. Down here, we're like, hey, for all the commands to register, just generate some text of what is the command, or how do you register the command with the system so that we know about it. And why do we do that? Why do we generate text? It's actually for debugging purposes. We don't have to generate text. We could generate syntax tree, but everything you generate goes into a file like this. This is for key map, but it's actually the same. So if you're stepping into a systems program in a debugger, you want to be able to step into generated code, just like regular code. And so when we generate code, it goes somewhere like this. And you know, when I compiled that game in 2 seconds that you saw, in addition to the 297,000 lines of static code, we generated about 3,000 lines of code as well and compiled that. I don't think I said this, but that's not an incremental build time. That is a full, clean rebuild. And the reason we don't do incremental builds at all, because I hate all the bugs that come with incremental builds. So, all right. So that's, I don't know. It's probably hard to make sense out of all these kind of details when you don't really know the language. And I'm sympathetic to that. So let's do some visual stuff. One of the things, one of the things I'm interested in the long term is just understanding code. We'll come back to this in a bit, but part of this has to do with this question of why do you think it's a good idea to do manual memory management? And part of my answer to that is, you know, back when I was learning C and some other systems languages and had all these weird bugs, a big reason the bugs were so frustrating and difficult is like I just didn't have visibility into what was going on. Like my program would behave weird and it would crash and I would sit there and have to debug it for a long time and like not really, like that debugging was a frustrating process because it's like grasping for scraps of information in a very difficult way, which actually also describes my semester of CS60A at Berkeley programming in Scheme, which is not a manual memory management language. But it's approximately as horrible in terms of debugging once your programs get complicated. I hate them so much for making me do that. All right. So this started as a weekend project. Whoops, I ran the wrong thing. I'm running the same game that we did. That's not what I wanted. I wanted this. This is a little program visualizer that I really threw together, but it's part of my long-term interest in understanding programs and making them more bug-free. And it will also serve as a good example of what is a use case for all this stuff that you just blazed through and talked about all these messages and whatever. And I'm just going to browse and load this file. This is a visualization of the program, and what it's doing is it's computing, or had computed at compile time, some metrics based on that information that was coming through in the messages, and then it saved that out into a binary file, and that can be stored in source control or whatever, checkpointed, and you can run the visualizer on that at any time. So what this is a static view of the code where every square, every leaf square is just a procedure or function. And The size is proportional to how big the procedure is. The size metric that I'm using is expression count, and so you probably can't come up really with a good size metric that makes everybody happy, but lines of code is obviously not very good because long lines and short lines and whatever. So if you just imagine a typed syntax tree of the program, how many nodes are there? That's approximately the expression count, and so things are bigger when they have more expression count, right? And so then the coloring of each of these is a code quality metric that I kind of made up, but it's a linear combination of a bunch of things. You can zoom on it, right, and just like zoom around or whatever. And then, people who use Emacs know that it's quite easy to interface with Emacs and get it to go to certain file and lines. So, if I somehow am on Multimon or whatever, and I just want to say, hey, what's this build lightmaps function? I can click on it and we go there and all that. So it's quite nice. So what is this code quality metric? It's a linear combination of things that you might care about in a systems program. So we can look at those things individually. So for example, do you have a lot of if statements or not, right? And so things that are blue are cold by this metric. They don't have very many if statements. Things that are orange are hot and have a lot of if statements. And this was done just because when we get this message that things are type checked, it contains the syntax tree of the program with type annotations on the whole tree. And it is an exported protocol stable version of the syntax tree of the program because the compiler needs to be able to change over time without breaking everybody, right? And so one of the things it's doing in that 2-second compile time is copying the entire program to like another format, putting all the data in there and letting you inspect it, right? So you can inspect as expression by expression. You can navigate the tree and look at it, right? So, maybe you like things that are less branchy. Oh, the other thing to say about these colors is they're normalized across just this program. So the most orange thing, which is probably here, has the most if points per unit size, and then the blue things. But there's no absolute metric in any of this. So like, how nested are your if statements, right? Are they nested? Are they not nested? How nested are your loops, right? Because n-dimensional loops can be confusing. Do you do a lot of assignments or not, right? If you're a functional programmer, you maybe don't like assignments to variables. Fortunately, a lot of this program is blue, so it's not really doing that many assignments, but some of it isn't. I'm sure everybody in this room doesn't like global variables. So like, hey, did you access global variables? Did you read from globals, right? Did you write to globals, which is probably the more important one, because that's what actually causes race conditions in threaded programs, is when somebody writes and somebody else reads and there isn't coordination on that, right? Although, things can be plenty confusing in other cases as well. So there's some really, right here, whatever this code is not that good about this. Okay, I wrote this code. It's fine. Okay, let's get back to memory management. So heap allocations, what parts of the program actually allocate memory? Now this is a static view, right? So this is, do these functions contain calls that could allocate memory or not, right? Do they free memory? Do they, if you have code inside a module, does it call within its own module or to another module, right? Same with a file. And this one's interesting. If you're calling a function, is that function known at compile time? Or if it's orange, it's like dynamic. It's what systems people would call a function pointer, right? But it's a function bound to a variable that you can't statically know what it is, right? So that's a lot of information to have about a program. And this is just sort of the metrics that we chose. There's a lot of stuff, other stuff you can do from this meta program, right? You can do error checking. You can do style checking. You can modify procedures and resubmit them and all that. So it's a really powerful mechanism. So let's look for a few more things. So over here, let's go back to the blend. So this is, again, just a linear combination of all those things weighted by how important I thought they were on the day when I did that. So I'm not saying this is the most important thing ever. But you might imagine that you have your own opinion about what things are more important, right? And because this is all, so the other thing to reemphasize at this point is, in some systems where the compiler author decided that something like this is important, they might like work with you and like give you some tools to give you some introspection about what the compiler is doing. None of that was necessary here. All of this information already exists at user level, and we're just visualizing it. So this thing on the left is the main program. All these black rectangles over here are like module dependencies to like what's sort of our standard library. And you notice there's a lot of uniformity here among these rectangles, and these are all co-instances of polymorphic procedures. So there's bucket array. Where's hash table? We're going to talk about hash table later, so there it is. So, this is like this function table add. I'll click on it so we can go look at it. You can't obviously tell that this is polymorphic if you don't know the language, but it is. And so for every type of hash table that you call this on, we generate a different copy of the function, right? And so there's a lot of copies of the same thing. And so suddenly I can visualize like how much is polymorphism costing me, at least in program size, right? So that's useful. And then another thing you might notice in terms of reining in enthusiasm over programming language features, there's some rectangle over here that's very conspicuous. It's like by far the biggest function in this program. And I use prepping for talks like this as a way to like, get work done. So I'm like, what is this? Why do we have this really big function? So I went and looked at it, and this was written by our summer intern last year. He's coming back to work for us again next week. So, hey, Burke, how's it going? So this function, it looks normal. It doesn't even look that long. Like it's a couple hundred lines. I don't know, 300 lines. So what's going on? But what's actually going on in here is, it has some sub-functions that it uses. That's not that surprising. Like this is another function definition. But actually this expand means that this is a macro, and this is also a macro, and this macro calls this macro a number of times. And then down here we call both of those a bunch of times. And so a macro expansion just like splats out the code, right? So there's like 50, 60, I don't know how many macro expansions in here. And I wouldn't have ever spotted that, right? But like this rectangle makes it very, very obvious. And so broadly speaking, I think the more clearly you can see your program, the easier it is to work on. The less mysterious bugs are going to be when you find them because you just understand the current state of the code better. And the fewer bugs you're going to have in the first place because when you add new code, it's within a domain of more thorough knowledge about the state of everything. All right. So I think, let's talk about memory leaks now. So we just showed this visualizer. My philosophy is to make everything as visual as possible. That includes common memory problems. Now the design of this language eliminates, as many modern systems languages do, we eliminate a lot of the C problems by just having an array as a fundamental type, which like C doesn't really have. Exactly. So in a C program, you're always like dereferencing through a pointer that has an unknown end. And so reading out of bounds of an array is like very common, right? Whereas in modern systems languages, you generally pass a bounded array everywhere. You can get a runtime exception, if not a compile time exception, when you go out of bounds of array. This is no different. But the kind of memory problem that is more insidious and that the Rust people will be very anxious about is memory leaks, where you just like allocate some memory and forget to free it. Now, you also have memory leaks in garbage collected languages. We had a talk yesterday that started with an anecdote about a Node.js memory leak, that there are enough of those that like people sell products because people search for it on the web all the time. So memory leak, common problem. Now, I have in the past paid for memory analysis tools for C++. And there's open source ones. And they have a few things in common. They don't always work, and they're really slow. And they make things run just at a really painful speed. And so one of my priorities when I made this language is like, look, okay, you got to make it good for finding these kind of bugs if you're going to have a non-managed memory language, right? And so let's run the example first. Modules, basic examples. What's it called? Yeah. So this is just going to output a bunch of spam. I'll just run through it fast and just say what it is. So we've got some sample program that does some trivial things about adding some numbers together. But while it's doing that, it's intentionally doing a bunch of stupid stuff with memory because this is a test of the memory usage system. And so then we generate a leak report in ASCII. And hey, somebody leaked 64K, right? And whatever. And this is with vanilla settings. You can see main is calling like copy string, which is calling some alloc and whatever. All these functions would be familiar to anyone using the language. So there's nothing mysterious here. And then in this kind of report generation, it can get very verbose very fast. Sometimes you want to group allocations together. So like we have a ton of allocations, but they're all through mostly common pathways. And so instead of getting a massive spam report, we want to just aggregate things that I think of as related. And there's two ways to do that. There's things that have common leaves, right, and things that have common roots. So an example of pruning leaves here to make the report nicer is, look, we know that copy string is a function that allocates, right? Even though the implementation of copy string calls like 4 or 5 things to do that, we don't need to see all that. Like we know from here. And so when you ask for the report, you can just say prune everything below this function, right? Similarly, you can prune roots. So like, look, we know we're from main because in this language, your program starts in main. So I don't need to see that. So you can also set an option where you just prune out main or any arbitrary set of initial depths, right? And then sometimes you've got some annoying function like a recursive function where maybe most of the time you just want to ignore the fact that it recurses into itself from 37 different places and you want to treat that all as one thing. But then sometimes if you're really debugging and getting down in the weeds, you need to know, did it go this path or this path? And so you can set that and all this stuff. Yeah, and then this is just grouping stuff together. We're going to show a better version of this in a second anyway. And then this is just making the point. All this is generated as a data structure, not text. My big beef with Unix is everybody likes piping text around and reinterpreting the text, and I think it creates a tremendous amount of friction. So this API generates data structures that you can just inspect and report in whatever way, and we're going to show a different way of reporting this in a second that's built on this same foundation. I'm not sure it's worth looking at the program that generates this, actually, now that we've explained it, but during the Q&A, we can do that if people are interested. Now, like I said in the beginning, one of the problems with these things is, well, there's 3 problems. One is there tends to be a lot of friction in open source versions of this or commercial versions of this because it's not your usual workflow. Yeah, let's look at just the top of this. So the way that you turn this on is you just do this. You just say memory debugger is true. Basic is sort of the biggest or the most basic component of our standard library. It's a thing that like gives you print functions and some string functions and like some memory allocation and all that, right? You don't actually have to use it because we enable you to run with very minimal dependencies, but most people will choose to use it. And so if you're using it, you just turn this on, and everybody who uses any allocator in the language now goes through these memory debugger hooks, which are quite fast. And again, that's the other thing that makes people not want to use these all the time, is that like maybe they instrument your code, or I don't know, like you compile a bunch of weird stuff in and it goes really, really slow. I come from video games, right? And video games, we do quite a lot of operations per every frame of the program. So here's what I'll do to demonstrate that this runs at a reasonable speed. and has different ways to visualize the information. So this is the same program that I opened, to start with that like showed this thing. I've got another tab here called allocators. You go there and it tells you, hey, if you want to use this, nobody's using this right now. If you want to use it, just do this in your program, right? And I just compiled a version of that same game that does this. I didn't show the frame rate before, but the game would have been v-synced, locked at 60 frames when I did this. Now it's 45, so we're taking a speed hit from this, but I can still play the game. Like, this is totally interactive, right? Okay, so what's happening while we're doing this? Well, we're getting a live report from that memory analysis tool every frame of how large is the current heap and what are all the specific allocations. And then these rectangles are allocations grouped together. Now, you may notice that this number of how big the heap is actually going up over time. There's a little bit of noise, but it's clearly going up. And that means there's a memory leak. And it's a legit leak, because like I said, I like to use presentations like this to get some work done. And I hadn't run this tool in a little while. So you don't just have to look at a moving thing like this. You can just record the data. Every little rectangle here is a frame, and the orange thing are frames that are more hot in terms of memory activity. And you notice it's kind of getting more orange over time just because the heap is getting a little bigger, right? So I can stop that. I can scrub across all the frames about what's been going on. And like, let's say I wanted to debug this. I just pick a frame. I can inspect what is the call stacks that allocated any particular group of so like I said, these little rectangles that I'm cursoring over are groups of allocations grouped together by these call stacks. And these are the same things that you saw in that text report, right? I can click on them. So if I want to know add animation to entity, where does that happen? I can click on that in my Emacs. My Emacs goes there and goes to the next call in the stack, right, to show me exactly where that is. I can restrict this. So if I want to say, only tell me about allocations that are through add animation to entity, I can right-click, and you'll see it's like getting rid of a bunch of stuff, but there's still quite a few. And as I click across these, all of them go through that node in the stack, right? But now let's get to our memory leak, because we're still leaking. The game's still running this whole time. So what's going on? Well, so this top rectangle again is the whole heap, everything in memory. It's about 370 megabytes, right? And then down here is per frame, because there's a little one thing that you call to help the tool aside from doing that import is you just call a function that says it's the next frame now, right? And it uses that to know what's each frame. And so during one particular frame, we allocated about 300K of memory, which is actually way too much. Again, it's my fault. I wrote this visibility culling code a couple months ago and hadn't rerun this tool since then. I actually since fixed it, but I didn't want to fix it here because we want things to talk about during the presentation. So, but right away I can see, okay, who's allocating? So in a game like this, you actually don't want to allocate a ton of dynamic memory every frame, because even though you go free it, you tend to, in a systems language, not use an allocator that relocates memory, right? Because you don't have a system that changes the pointers. So when you free memory, you have holes in memory that need to be reoccupied later, right? It's not like a generation scavenger or anything like that. So you want to avoid this massive fragmentation that happens, because it could cause you to run out of memory, practically speaking, even though you've got a bunch of little holes that comprise some amount of memory that you wish you could use. And that's especially true on fixed platforms. So, on a PC, it's not that bad, but on a video game console, there's no virtual memory paging, right? So if you run out of RAM, you can't magically get more out of the ether. And so we care a lot about these things. It's one reason why garbage collectors are not very popular among high-end video game people, although independent people use Unity game engine all the time, and that's usually garbage collected. All right, but anyway, if I wanted to debug this leak, it's actually very simple most of the time. I can just say, what was allocated this frame but also not freed this frame, right? And it's a little under 1K, and it's in this function compute options hash, and I can click there. Again, I'm at compute options hash now, and whatever, and I can just fix the leak. It's a very simple function. You just have to free the string. Actually, what it should be doing is doing its string operations using a temporary allocator that doesn't go to the general heap is the correct fix for that in the way that we program our stuff. But this is very powerful, is my point. It's very useful and very powerful. And there's a lot more that you could imagine in terms of like visualizing this in different ways, right? I almost would like, I would like a view maybe, zoom in, more like this, that's easier to see all at once rather than this linear thing. The only thing stopping me from that is I'm just not sure how to hierarchically relate memory in that way. Like how big is memory is obvious. It's how many bytes. Oh, that reminds me, there's different things. So this is sorted by bytes. You can sort by how many allocations are there, how many bytes per allocation. So if you're allocating a lot of very small pieces of memory, that's relatively inefficient. If you're allocating bigger pieces of memory, that's more efficient. So in this sort, things on the right are better, right? So things on the left are better. I always get my sorting functions backwards sometimes. This is a 2 megabyte allocation, and as you go over here, it's like, 128 bytes per allocation, which is not very good. And then some of the other stuff we could have looked at down here is like what got created and freed this frame, which you might think is better because at least we freed it. But this is actually very spammy as well for reasons I discussed. And also just like you're writing a bunch of memory and then throwing it away every frame. It's obviously faster if you do less work. And so this can help you find things that are inefficient, right? Are there things that were freed and not new? If you see something like that, it's like, oh, there's something with a legitimate long-term lifetime. It's probably not a bug, because if you got a bug, it would have exceptioned your program and stopped it, right? But you can have things with legitimate long-term lifetimes, and then they get freed at some point down the line. And that does happen in this game for sure. But if you see a lot of that, it means your frame rate's going to be kind of spiky, because maybe you have work that happens on some frames and not on other frames, and that's a thing that we like to avoid in games. So, these are just ways of having more information about your program. And my goal has been to build them into the system in a very low friction way so that everybody has access to them. Nobody has to pay for them, but also nobody has to use some weird low effort open source thing that nobody really cares about. And because I'm done suffering that pain. I've suffered so much through those things. All right, so we got one last thing that we could talk about, which is just, we care not just about performance during runtime, but also compile time, right? I mentioned that it takes about 2 seconds to compile this on this laptop. That's pretty fast compared to most systems. The goal of this system is to be fast, though, and so we're targeting being an order of magnitude faster in the end. That'll take some doing, but it is possible. But when you're not a compiler author, you're just someone writing a program, a question you might have is like, hey man, it's taking a long time these days to compile my program. What can I do about that? And there's a little module to turn on compiler performance report. So here's our command line we did before to build the compiler, and I'm just going to add a -perf on there. And it's going to take about the same amount of time. And it's going to give us, hopefully it's all in the scroll back. Yeah, it's going to give us a lot of text about what operations did the compiler do. And this is a work in progress, but it's already pretty useful. I already used it, again, prepping this talk to fix a problem that I didn't know about. So the first thing that we see here is the run report. I already mentioned before that a lot of the compiler's functionality is based on compile time execution. compile time execution takes two forms. One is there's an external metaprogram, like I was saying. That runs in parallel with compilation, so for the most part, it doesn't really slow you down. But inside your own program, you can say, you know, x equals the result of some compile time execution and bind that, right? And those obviously take some time, and you can't compile the program further until you know the value of that variable, right? So we tell you how long did all of those take together. In this case, 0.04 seconds. We spent 0.015 seconds, or 0.04, did I say that? 0.015 seconds inlining things, and 0.17 seconds actually generating the bytecode for functions. Most of our time is spent in type checking, actually. Or when we're unfortunate enough to use the LLVM backend, which we do to optimize right now, that takes a long time, regrettably long. But anyway, so this is a list serially of all the compile time executions that happened. It looks like a lot. Actually, two of these, the problem that I noticed is we actually have two different things that are going through and instrumenting a bunch of functions with profiling information that we use in a runtime profiler that I can show, again in Q&A if anyone cares. There's this one and this one. And so there's a ton of instances, because each time one of those sees a function it wants to insert profiling data in, it does a compile time execution. But then there's a bunch of others that have to do with regular things. Okay, and then the other thing that's useful here, we don't have timestamps on this. I want to put them in. It's a little more involved to implement. But this is the polymorphism report, right? So like, how many times did you do a function call that potentially involved polymorphism? Because you could have overloading between a polymorphic and a non-polymorphic function that are bound to the same name. And you got to figure out what's the better match, right? How many times did we run the solver? And then how many times did that actually result in something that was the correct match? And then for every individual function, we talked about hash tables, so let's go. Here's the table add function that we looked at before. Wait, did I go past it? Table add. Here's the table add function, and here's where it is. You called it 515 times in the program. 427 of those used polymorphic variables that matched something that was previously generated, so they cost you the solve, but they don't generate more code, right? But then here's all the polymorphs that actually generated new code, right? And this is information that you could have put into that visualization before, but like I didn't somehow. So for each of these, you have like, okay, this was a hash table mapping from string to signed 64-bit, right? Here's a hash table mapping from a pointer to a material, where a material is just one of our data structures, to a bool, and so on. And so you just get like, here's all the things, right? And you get that for every function. And so if you see something crazy here, you can be like, oh, that's not good. I want to change that, right? And I mean, the polymorphism really does add up. Like, it's a powerful thing, but it costs you a lot, is all I would say. So you want to keep an eye on it and make sure it doesn't go crazy. So those are other ways of seeing code as data and having more data about our code, right? Visualizing our code better. So I did all this. So my closing point, and then I wanted to leave ample time for questions. I'm not sure what time we can go up until. We'll let them cut us off if anyone has questions. But my final point is that you can view my design decisions on this language as being a different way to approach cost-benefit analysis, right? So usually the way that programming language design goes, and the way it went in some cases here, is, hey, I've got a cool new idea for a feature. Don't you want this awesome feature that I'm going to advertise to you? And a good engineer should say, well, maybe, right? What does it cost me? What does it really cost me? Like, not just in terms of the things you don't want to admit, but also hidden costs, right, that maybe take sometimes even years to understand, right? And then what's the benefit? And what's really the benefit, and not like the fake benefit that you're advertising and all that, right? So good engineers are doing cost-benefit analysis all the time. And so one of the reasons why systems languages with manual memory management got such a bad rap is that there were legitimately these huge costs, right? I mean, I had so many lost, all-nighters, especially in college, being miserable about why my C program wasn't doing what I thought it was, right? And that's obviously terrible. But so the thing is, one tactic of approaching a cost-benefit analysis is to try to provide people new benefits that have low cost, right? Another way of working out this equation is to try to reduce the cost of what you already had, right? Hey, we've got this thing, we're paying so much for it, can we get it cheaper, right? And if you can get something cheaper, then the cost-benefit analysis changes, right? The inflection point at which something becomes a good idea will change if the costs go down. And so I've been trying to reduce costs of manual memory management, among other things. And so, it's just to say the accepted wisdom of what's a good idea in programming language design and what's in vogue and how memory safe you need to be worried about, you need to be, and all these things is based on a cost-benefit analysis where the costs were kind of decided in the 1980s or early 1990s and haven't been seriously approached since then. And regardless of, your conclusions, I think it's well worth doing an honest assessment of this cost. Like, look, what is a systems programming language like if you actually put in the frickin' work to remove the friction and the landmines from all this stuff, remove all these problems that don't have to be there? What does that look like in the end? What do you get? What is it like to program in? And honestly, nobody's ever done that. I think people think they do it, but it always gets weird and, just runs away with things. And then you have languages like C++ that are committee-driven, mostly by people who don't write what I would recognize as real software, right? And so that's what I'm really trying to do, is just make my contribution to what could this stuff look like. And I guess we'll take questions at this point. Do we have a roving mic? Great.
So I like the way you're approaching the cost-benefit analysis and reevaluating things like memory management. But one of the things I haven't seen in a lot of the modern systems programming takes is reevaluating what it means to do some of the more esoteric things on the CPU or the GPU or things like that. And I find that they tend really like SIMD operations or getting access to the more what are modern features of the CPUs. It doesn't seem like modern systems programming is doing that much work improving the ergonomics of accessing those parts of the CPU. Do you have a thought on how you might address that? Are you thinking about that at all?
This is one of the primary things that I worry about still, because it's even harder than you said, actually, right? So traditionally, if you want to use SIMD instructions in C or C++, or really any language, it all basically works the same. There's a set of functions called intrinsics that map more or less directly to assembly language operations, and those are provided to you, in some library, and you just call those, right? And there's nothing. You're basically kind of programming in assembly with a little bit of syntactic sugar, like you could use variables and stuff, right? But that has been the state of the art in doing that since the 1990s, I'm going to say. It hasn't, or whenever Intel did the MMX instruction set, which I believe was late 90s, and maybe even before that. So the thing is, what I've been thinking about is can you provide, because I never really believe in a golden panacea that'll automatically compile down in all platforms to the right thing, right? And so it needs to be, someone, I forget which talk it was in. It was in the talk about programming language power yesterday. The speaker said, one thing about power is it's not about being super high up in abstraction or super low down. It's about going where you need to go at the time you need to go and being able to do that relatively easily. So if you want to have lots of high-level expressivity, you can. But if you want to address very important details, you can, right? And I think that is what a successful solution would look like. The problem is, as we're trying to solve this, CPUs are becoming ever more heterogeneous. So you have, like, SIMD widths were uniformly growing for a while, and then, like, AVX 512, like, kind of didn't work, and new CPUs don't even support it a lot of the time. And then you've got tensor cores, and, like, what should we be trying to address that with the same system? And so all I can say is, like, I'm actually having a meeting Thursday with somebody from one of these AI chip companies, and I'm just having conversations to try to figure it out. Like, you could imagine some form of intrinsics where there's a bunch that you could use that are remappable. Like, 8 wide add is probably going to work everywhere, right? Maybe. And so maybe you can use a bunch of those, but then, like, if def in specific cases, I've yet to be convinced that that's really super solvable right now, but we're looking for the solution. Yeah.
Once you release this language, I'm wondering if you add new features or even change how the compiler works, I'm wondering how you would change modules / compiler or version it.
Yeah, so here's what I have to say about that. There's a bunch of sub-answers to this question depending on magnitude of the change, right? One thing that I don't like about C++, which was the primary language that I had to use before I made this, is its backward compatibility forever, and they make quite large decisions. And a lot of what C++ now is doing now is adding complexity to kind of but not completely fix bad decisions that were made in the past, right? And so it's like you end up in this thing where you keep heaping trash on a thing. You know, having some experience in graphics, I'm much more of a fan of the DirectX graphics API model, which was, you know, hey, you made a game for DirectX 5, which is just an API with certain data structures and certain things, but graphics is evolving rapidly. So we're going to release DirectX 6, and it's similar, but it's not trying to be backwards compatible, and we'll support 5 for a long time, but at some point you explicitly make the jump, right? So that is the model for that. And then when it comes to modules and all this stuff, you know, we have modules that we provide with the compiler, but you're free to copy them into your program at any time, and they work. And so you can essentially freeze one just by copying it locally into a subfolder. That's, you know, I'm very anti this whole, like, NPM thing that happened where all these web people, like, not only is their program, like, not a mathematical object, it's, like, defined by things not even on their computer, like, out in the world that might change at some point or go away. Like, that's the worst possible reality. And so I think you want in source control, ideally, everything that you're using. So if you're using a bunch of modules and you add a new one, you know, hopefully you copy it locally at some point. And so as long as the core compiler is not changing radically, that all makes sense, right? Just to protect yourself against revisions of modules. And then for big compiler changes, like I say, I would like to do you know, backward compatibility for simple things up to a point, and then some kind of breaking change. You still can use the old compiler if you want. And then the thing that is in the thesis but we haven't tested yet is all this metaprogramming capability that I showed. It's more than enough information to just rewrite your program. Oh, and one thing that I should really emphasize about all the stuff that I demoed is, you know, sometimes you see systems where people had a visualizer or something and it worked by, like, they parsed your program text themselves and looked at what all the functions are. And anytime you have a system like that, it either has to re-implement the entire compiler or it will get things wrong sometimes, right? Like, oh, you use this variable name and I thought it was this function, but it was this other function here, right? The reason that we pass these messages to you after they've gone through type checking is because to do type checking, you have to resolve all the identifiers, right? You have to expand all the macros. You have to do all this stuff. And so there is no ambiguity about what is referencing what with what syntax or anything, right? And so once there's no ambiguity, you can rewrite the program. And so the earliest version of the compiler actually just outputted C code, right, before we wrote our own bytecode. So it's relatively easy to transpile, relatively, because the difficulty of transpiling often just depends on how close are the concepts of the target language to the source language, right? If there's things in the source language that are really hard to express in the target language, you might have to do a lot of shenanigans to make it work. But in successive, like, breaking revisions of one programming language, you would expect it not to be that crazy. And so the plan would be that we provide a metaprogram that'll just convert your code to the new thing if you want to use it. And the actual hard part of that is like not messing up the indentation and all that. And comments, and because comments aren't in those messages, and like, so you have to do some hybrid of looking at the text file, saying like, okay, I have semantics of code from this point to this point, and then let's paste in whatever was between that and the next thing, and we just haven't done that yet, but that's the plan. Yeah.
So I switched from chemical engineering to software. And something I really, really miss is an ability to figure out the efficiency of things I'm doing. So for example, if I'm designing a chemical reactor, I know what the ideal amount of something I can get out of it is. And I feel like with software, I have no clue. Like I use Java at work. Yeah. I know it's slow, but I have no idea what the trade-off is. And it's really difficult because, you know, when you talk to management about things, you're like, I'd rather have a better language. But then they're going to say, well, is it really worth it? And I have no ability to tell them what we're losing. So I like your idea of like, oh, like put it out in front of me. I want to see it. I suspect the answer to this is no, but just in case you've thought about it, do you think it's possible to kind of get an idea of the efficiency at runtime as well?
So relative to the way most programmers think, yes. So relative to the way most programmers in the world in the year 2025 think, if you just do a good job on cleaning up these visualizations that I showed, and like if things spike up really slow, I didn't show, so we have some other stuff. So I showed memory stuff, but there's some other stuff that we have built into the game that everybody gets. Well, one of them everybody gets. So like here's a CPU profiler. Remember when I showed all those compile time executions and it was like it's running this stuff? So this tells you how much time is being spent anywhere in the program, and so I can sort of cursor through and like hierarchically navigate this. And it's very convenient that it's on top of what I'm playing, because I could actually play the game while this is going and see if I'm doing things that cause spikes or whatever, right? And then we have that for GPU as well, where you can sort of like freeze the frame and like what's happening on the GPU, right? Like we're drawing translucent things, it takes a millisecond, is that good or not? So up to that point, we provide all this information. Now the question, is 1.3 milliseconds too much time or not? What is the ideal time? The problem is just that depends very heavily on what exactly is the hardware you're running on, right? So let's go back to CPU for a minute, because maybe more people are familiar with that. You know, what's your model of CPU, and like what's the L1 cache size, right? And the answer to that question determines a lot of things. And so there are people who care a great deal about this in games still. Even in games, this is becoming a minority of programmers though, because things are so complicated that people are just barely getting things to work. And you need to have this extra effort and energy to do what you're talking about, right? And most people just fall down miserably tired because they finally got their thing working, right? But there are some people who do that, and they're pretty hardcore. That hasn't been my focus here, just because that would involve creating tools that have a lot of specific knowledge about very different hardware, and to some degree, that would be duplicating things that already exist. So, you know, if you go, for example, design a game for the Sony PlayStation 5, current one, they have a tool suite that is quite good at helping you answer this kind of question for that specific console. And there's a bunch of great visualizations and all. Like, the stuff that's in the games industry when you care about performance is so far beyond like what's in the public sector, nobody has any idea, right? And so those things already exist. So maybe you would enjoy game programming from that perspective, but it's also very hard.
Wow, there's a lot of questions here. So
I'll try to be
we might-
faster in answers if that'll help. I don't know if we even
that
have
might,
many
might
more
help.
questions.
We might take another like 2 questions
All
unless.
right.
Could you expand a bit on ergonomics of allocations and allocation strategies in J?
Yeah, so one of the things I was miserable about in C++ is, C++ has a heap allocate. You allocate things on the heap with malloc or new. That's like a global allocator. Modern systems programmers will tell you that's a bad idea. That's like a bad abstraction for a bunch of reasons. All your data gets tangled together regardless of lifetime and whatever, right? But also the thing that's not ergonomic about C++ is like, you kind of, if you want to intercept those calls and do something with them, it's actually really annoying and difficult and operating system dependent. And again, the tools break and they're slow and they're annoying. So what we do is, so our function that allocates memory reads from this thing called the context. The context is, so if you know C++ is like object-oriented in this sense that like there's a class that's the active class and it gets passed as the implicit invisible pointer at the front of a function and all that. So the context is like that, but globally across the program. We actually don't do objects in the C++ way, right? And the context has things that are useful for everyone. It has a pointer to the current allocator. It has a pointer to the current logger and all that. And so if you want to replace the allocator, all you actually have to do is just swap out context.allocator. You just push a new value onto that. And then any code that you call until you set it back is now using the new allocator. And then again, so here, right here is where that memory debugger stuff hooks in, right? This is a static if, so it doesn't have any cost if we are running a release build. And so if memory debugger is turned on, just do whatever you're going to do to check this allocation. So this works as long as you're using an allocator that conforms to this mechanism that everybody wants to use because it's so understandable and convenient. It'll go through all that stuff, all those tools that I talked about will work on it. This doesn't see, if you're using like, let's say a graphics API that allocates its own memory behind your back and it was written in some programming language you don't know, this doesn't see that, and those tools won't see that. But you could write something that snoops that and shares the data, but that doesn't feel like my job, right?
So it seemed like the memory leak that you were debugging was in a function that related to shader monomorphization. I might be wrong, but I was wondering if you have some thoughts on compile time versus runtime monomorphization for GPUs and shaders. Because it seems like a case where the compile time polymorphism explodes into too many permutations and variations to ship it.
Yeah, I mean, this is a problem across games right now. So like back in the 1960s and 1970s, like when C was invented, we knew that you could run a program in one language across a bunch of architectures. And now that's not even true. So like if I have an NVIDIA GPU and I'm running on a Mac, I have to use a different programming language for my shaders than I do if it's the same hardware, the same CPU and the same GPU running Windows or Linux, right? It's a so that's one level of permutation. Is like I have to have entirely different programming language because the drivers don't take anything lower level than that. They take text, right? And so then there's another level of combinatorics where like, okay, I want to generate this shader, but I want it to be efficient, so I don't want to include a bunch of code that doesn't need to run in a lot of cases, but I need that sometimes, so I need to generate permutations of the shader. And so we end up essentially pasting text together and feeding it to the graphics driver, and you generate an explosion of variants of shaders, and this annoys everybody, including people who want to play the game. And they load up Call of Duty, whatever is the most recent one, and you sit there and it says compiling shaders on the screen for literally 2 minutes. And it has to redo that every time you update your graphics driver because they'll have the wrong, because there's a compiled version of the shader, but it's like stamped for like what version is everything, and as soon as anything doesn't match that, it'll recompile. I think that's a giant disaster. I think it's completely stupid. I don't have a way around that from a systems level because it involves all these technical decisions that are made by people who want to protect their walled garden and all these things. We do, though, if I take off my compiler author hat and I put on my game developer hat, we work pretty hard to keep those permutations down, right? So traditionally, you want to be branch free is the common knowledge and or the common wisdom, and you want to avoid if statements and all that. But actually, if statements are okay if they're on a uniform that has a constant value for the entire thread warp and all this stuff, right? And so, we're gradually learning to have fewer and fewer, compile time variables in the shaders. But it sucks. It's not, none of it is good.
All right, we have time for one final question. Who's going to be the lucky person? Two people both here raising your hand. Maybe you should arm wrestle.
I think you need to throw the mic up in the air and whoever catches it.
A question about the game business.
Yeah.
If a person was an indie developer today, there's all these different platforms that you could be published on, and when you have a tiny budget, you kind of have to pick one to start with. There's Nintendo and Xbox and PC download. Where can you actually earn money as slices of the pie? How does it settle out? Because you're on many platforms.
Yeah, that really has nothing to do with the talk, but I do have an answer for you. And this is going to get console people mad at me, but the thing about if you program for a specific Nintendo console or a specific Sony console, you're at the mercy of their store. Do you get placement? And then you'll go out of date when there's the next console. Even on iOS, like Windows, for example, was this operating system that did a really good job at being they would sweated so you would be backward compatible. They would run, programs from 30 years ago on versions of Windows that didn't even have protected memory and whatever. And iOS invalidates your game every 6 months or something. It's a chore. You have to constantly be on top of it to keep things on the store. So I would say, honestly, Windows PC, and there are a few stores. There's Steam, there's itch.io, there's places like that. It's the most, because you're actually in control of your program won't decay like a sandwich and get moldy on PC in the same way as it does on other platforms.
All right. Thank you so much, Jonathan.
Thanks,
Let's
everybody.
give it up for Jonathan Blow.